Let me welcome you all to this second class on analog IC design. Today we'll be talking about MOSFET single stage amplifiers, part 1. Okay, because it's a big topic, I'll touch upon half the portion today, and rest of half I will tackle in the next class. Also, I'll be demonstrating whatever we learned, we are going to learn today in LT Spice also, okay, so that you can relate the theoretical part with the practical aspects. Okay, the large signal model, first we are going to see a MOSFET large signal model. This is based on this book, Cedra Smith. Okay, this we saw in our VLSI design class, that when we have a small VDS, okay, this is how the current and the VDS plot looks like, where the current is an linear function of VDS, and this is the equation which is given, and this resistance can be varied by changing the overdrive voltage, right? Somebody had a question, or it was just a noise? Okay, this was what for small VDS. We did the derivation also in the last class, and then as we increase VDS, then the equation changes as ID is equal to so the equation gets modified in this manner, right? And then we further increase the VDS, it gets into the saturation region, right? In the saturation region, for long channel devices, we can say that the currents are independent of VDS, but for short channel devices, that is not the case. We also saw that in our previous class. Okay, so this is the current equation, which is in the bottommost, which is given, which is applicable for saturation region for long channel devices. For the short channel devices, one more component, 1 plus lambda VDS is there. Okay, and now when I do circuit analysis, okay, the MOSFET, we just replace the MOSFET with its equivalent circuit, and then do normal electrical circuit analysis, which we did, right? Ohm's law, like KVL, KCL, that's all. So it is very analysis of all the MOSFET based circuits is only these three: Ohm's law, KCL and KVL. These are the things which will apply, right? Here there's no additional things which you need to know. Only thing which we need to know is how to replace the MOSFET with an equivalent circuit. So this is the equivalent circuit for large signal equivalent. I'll talk about what is large signal equivalent. Is the DC voltages what we apply for biasing the transistors. Okay, so this is VGS. Okay, this is half K, and this is the ID equation, right? This comes from the ID. This is for the saturation. In the saturation region, this is going to be the model for the MOSFET. Is this model clear to all of you? If you see here, we are applying a gate potential. There is no current which will flow into the gate. Okay, there will be current which will be flowing between the drain and the source, and the value of this is been replaced represented as a current source here. Why is this is square? Because it is a dependable current source. And what is it dependent on? It is dependent on VGS minus VT. Okay, and this is the exact equation. So this is known as the large signal equivalent model. Is it okay with all of you till here?
Yes, sir.
Can you please explain?
Yeah. The question is, why is it known as a large signal? Okay, it is why we are calling it as a large signal. This is the DC operating current. Okay, first we give some. We are not changing any voltage here. Okay, we are not. We have not yet talked about a small signal. A large signal is DC operating point. Okay, it may be a little bit vague. Let me go ahead by another 2 slides, and if it is not, what is the difference between large signal and small signal, it will be very clear. Okay, so this is a large signal equivalent circuit. Okay, now we find that, okay, these for short channel devices, these curves are not in a straight. They come and merge at early voltage, and we know an equivalent resistance R0. Okay, and we know the formula to compute an R0. Now R0 is dependent on ID. Okay, remember that. Okay, and it is also a function of L. So R0, R0, what is R0? It is like if you change in VDS, what will be the change in ID? Correct? R0 is slope of this curve, right? So for a small change in VDS, what will be the change in ID? Okay, that is R0 or VDS divided by ID. Okay, this is R0. So I am going to put one R0 out here, so that this is the additional current which will flow, right? That R0 will cater for this slope. Okay, understood why this R0 has been inserted here, all of you? Understood why this R0 is there? This R0 caters for this slope, okay? The additional current which is flowing. If I don't put this R0, this curves will be straight. R0 indicates that as you keep increasing VDS, current is flowing, right? So that comes through this resistance. Okay, so this becomes the large signal model MOSFET equivalent. Okay. Now this is for the NMOS. So this is one symbol of NMOS. This also is used. Okay, this symbol is also used many places. This is for Pmos. Okay. For the Pmos also it is the same. Okay, the symbol will be only thing is the source is on the top, drain is in the bottom. This is the current direction R0. Now it is a source drain voltage and source gate voltage. Okay, so that is there. And since you are taking source gate voltage out here, okay, the threshold voltage of an Pmos will generally be given in the negative. So you have to take the mod here to get the current. Okay. So this is the Pmos equivalent model for large signal. Okay. Now these are other symbols also which are used in certain textbooks. So for the enhancement mode, this is N channel. So you have a channel which is shown in the broken, and then you have a substrate connection here. For P channel, this arrow comes out. And for the depletion, this is shown as a straight line. Okay, this is the convention used because there is no breakage here. It is assumed that initially the channel is fully formed. So this is one notation which certain books follow. Certain other books follow the other notation. For the depletion, for the enhancement mode, they show a straight line, whereas for the depletion mode, they show a thick line. Okay. So this is another notation. So we have to be careful with what it is. Okay, whether it is. So there is like this is actually for in McGraw books. Many of the books you will find that this is actually an enhancement, whereas here it is actually for depletion. So from books to books it varies. So you have to be careful with these symbols out here, right? Now small signal equivalent is, okay, this is the small signal equivalent. Okay, that is you are applying a small change in VGS. Okay, then this current out here will be GM VGS. Okay, this indicates, okay, this is small signal model. Okay, what is this small signal model? GM VGS, it means for a small change in VGS, this is how the current will change. Okay, this is not ID equation if you see here. Okay, this is known as small signal equivalent. Okay, so let me first derive the equation for this, and then we will come to these diagrams. Okay, now VGS is actually capital VGS, which is the bias voltage which we give, right, plus a small voltage which is going to change the a small signal. Okay, I think I will show you one more diagram. Okay, this is the MOSFET, right? So I suppose I am using this as an amplifier. Okay, I can't give 0 to 1 millivolt to minus 1 millivolt. This will not get switched on at all, right? Because say 0.6 is the threshold voltage. Suppose 0.6 is the threshold voltage. If I give us 1 millivolt signal, then this will not be switched on at all. So what do? I have to give some DC voltage. Okay. So say suppose I am giving, and this is an 3 volt here. I give say here 1 volt. Although it's written 3 volt here. Suppose I give it here 1 volt, and then I give 1 millivolt small signal. So this will continuously be on. Okay, at 1 volt. Okay, and then this small change will get reflected as a change in ID here, right? So this VGS is the DC voltage which is written in capital. This small VGS is the AC signal which I am superimposing on this DC signal. This small I capital D is the total current, I capital D is the DC current, and small I small d is the again AC current. Is this thing clear to all of you?
Sir, I have one question.
Yeah, tell me.
How small this VGS can be? I mean, when we call it the small signal compared to large signal.
No, it will be generally in the order of millivolts, right?
When we compare it to DC voltage, I mean, some percentage is there?
No, it's not there. It depends on the generally small signals will be not necessary. When you are doing some power amplification and all, this can be large also.
Okay.
Right? Okay.
So is there any constraint on this with small VGS?
Yes. Right? Because when we bias these transistors, okay, we bias it for say for in a saturation region, you cannot give a signal very large that it comes out of the saturation in a circuit, then the signal will get distorted. Understood?
Okay. Right? Yes, sir.
Right?
But sir, after when we bias it this MOS in saturation region, there is a huge range of the VDS where we can, I mean, where this MOS can lie in saturation region. So that much big signal can be given.
Yeah, that can be given, but the more VGS you will draw, you will find that the signal is not a linear. So depending on application, you can do that. There's no issue.
Okay.
Can it be said that when we are talking about small signal equivalent, we are considering noise component in it, and when we are talking of large signal equivalent, there is no noise. There is just maybe a DC offset there.
Not noise. The actual signal is small signal. See these DC currents. Okay, we are giving these DC signals just to ensure that this MOSFET is in the required. Like I said, if I don't give the DC signal out here, okay,
for biasing
this
for
biasing
small VGS.
Yes, correct. Right.
Okay.
So when I say small signal, it is the AC signal. Now for the change in AC signal, what is happening? Okay, when I say large signal, it is the DC signal, that is the biasing and operating point signals. Yeah, tell me.
Sir, can you give an example for small and large signal which we can relate into a kind of relatable into anyone's life?
Yeah.
Just to clear an understanding on these two things.
Okay. Suppose this is a common source amplifier. Okay, here I am going to pick and say this is an audio amplifier. If I put a mic out here, right, the mic output will be in few millivolts, right? So you will get at least 10 times the amplified output here, audio signal, right? So that will be known as the small signal. Whereas for this MOSFET, if I give just a few millivolt, this MOSFET will not be switched on at all. So I have to give here say because this is say 10 millivolt, plus 10 to minus 10 millivolt is the voltage which is generated by the mic. Okay, so if I put it here as a 0, this will be off only. This will never come on. So instead of that, if I put say 1 volt here, okay, when this signal gets superimposed, it will go from 1 to 1.1 and it will come to say 0.9, right? So that 1 volt which is known here, which is given here for biasing, will be known as large signal, and this mic voltage which is coming here will be known as small signal. Is it okay now?
Yeah.
Sir,
Yeah, tell me.
Sir, I had a doubt. With this VT threshold voltage will always be overcome by this large signal, like VDC, which we are going to get.
Yeah, correct.
Okay.
Correct. So the bias voltage is essentially to overcome the threshold voltage. And also the bias voltage has got other that will decide the overall current which is flowing in this, right? Constant current which is flowing in that. Okay, we'll see that design aspect today itself. Okay, so let me come back to this. Okay, so this is the small signal equivalent. Okay, now to find out what will be the value of GM. Okay, so this is VGS, small VGS is capital VGS plus small VGS. Okay, this is the biasing voltage, this is the small signal. The total current is ID plus lambda ID, right? Now I have ID is equal to mu VGS minus VTH plus 1 plus lambda VDS. Okay, this is the equation which we studied in the last class. Now this VGS, okay, I can write it as VGS plus small VGS. Okay, and this is square. So I guess there should be a okay, it's okay. So this VGS I am writing as VGS plus small VGS. Okay, so I can write it as VGS minus VTN the whole square plus 2 VGS minus VTN. I think these things should have been in suffix. Okay, this T. Okay, plus VGS square. Okay, I am expanding this, right? Okay, these values. Now this is constant, right? DC voltage. This is something which has got a variable, that is small VGS. This is again a variable. Now this VGS is very, very small. Okay, so square I can neglect this. Okay, this is a constant which if I now I am going to find out the change in VD with the change in VGS. Okay, that will give me GM. So if I do delta ID by delta VGS, this term vanishes because there is no, this is constant. This term is square of VGS, which since VGS is small, I neglect this. So I just do the derivation of this. So right. So this VGS vanishes off, and this 2 and this 2 gets cancelled. So this is the value of the GM which I get. Okay, and this is GM. So now if you see here, if I neglect this channel length modulation, this is the equation which I get. Okay, now in this is this how GM has been computed, and is it clear to all of you? Anybody has got a doubt?
If the small signal VGS is comparable with the DC VGS in that case.
Small signal no, this VGS is DC operating VGS for computing of GM. Okay, this is capital VGS, right? Okay, this is the DC signal. This is GM. Okay, this is here. So this GM gets replaced by this particular equation, and here now for the small signal equivalent, this will be small VGS and small VGS. Although it's written capital here, this will be small VGS and small VGS.
Like my doubt is if like for smaller length we have threshold value lesser, so VGS also will be lesser. DC VGS, capital VGS. So in that case, it may possible this small signal will be comparable with the DC VGS. So like in such a case, GM will be depending on the small signal VGS also, right?
No. Okay, because accordingly, if you are talking about small channel devices, generally they will be in volts region, and this will be in the small will be in millivolts or microvolts. Okay. So is this now from here in this equation? And
Sir, I have one question.
Yeah, ask.
Sir, when we are differentiating ID with respect to small v caps VGS.
Yeah.
So how in this GM term this gets converted into capital V caps GS?
Because see, this is ID equation, right?
Yes, sir.
Now I am differentiating it with respect to small VGS. Okay. So this term is common, so it will be there. This term is also constant. This term only variable is there within this square thing, which I have expanded it here into 3.
Okay.
Right.
Okay.
So the first term is a constant, right? It is 0. The second constant is negligible, and this, if I differentiate, this small VGS goes. So I get it this way. This 2 and this 2. Is it okay with all of you? Yeah. Okay. So yeah, tell me.
In the previous slide, can you go to previous slide?
Yeah.
How we reach to this model A, like
see, this is small
GM
VGS.
into VGS.
This is small VGS.
But like how we got to know that this is GM into VGS?
This is what we got, right? Now, current is what is current? DI by VGS, right? So that is what it is, right? Current is GM into VGS, right? Small VGS. GM is what? Change in current with respect to voltage, right? So this is what? The current with respect to VGS.
Okay.
Is it okay? All of you?
Yeah.
This is okay? This is okay. See, there are...
Sir, I have a question on the previous slide.
Yeah.
Normally, a specification in the MOSFET is provided predominantly for the large signals. It's the RDS on parameter. So, is it right to say that this RDS on from the suppliers is in fact the parallel combination of all three, or it's just the R0?
No. R0 also depends on what is the length which you are for if you are taking a MOSFET, okay, a discrete component, the length is fixed, so R0 gets fixed there, right? When you are talking about VLSI design, L is a variable for you, so you can change the value of R0 also.
Okay. And sir, for large signals where we will have the application in let's say discrete circuits, so the RDS on parameter, is it exactly same as R0, or
no,
it's a parallel?
If RDS on means on is when the channel, when it is switched on, what is the resistance?
So there is no correlation with R0.
No.
It's only related with the transconductance.
On
right?
resistance, yeah, on resistance of the channel it is. Okay.
The slope of the graph that you mentioned.
That is actually that slope. This is VDS. The slope of the graph. So R
so then
on,
is it
correct.
to say it's R0?
R on. Yeah, you can call it as R on. You can call it as R on. Yeah, for discrete component, you can call it as R on. Okay. Yeah. Okay. Is this a value of GM and this particular one circuit, is it clear to all of you? Okay. Now let's focus on this. Okay. We will require a greater GM for greater gain. Okay. Isn't it? Right? If you are applying a small signal, if there is a large variation of current here, it will result in greater gain. We'll see that also, gain equation also subsequently. But it is desirable that GM should be high. Now for GM should be for high. Now if from this equation, if I just substitute the value of an ID, neglecting the channel, I will get this equation also. Now if you see here GM, if I increase the DC operating point, will I get higher GM? Correct? Isn't it? Anybody? If I increase the,
it will increase.
It will increase, right? Similarly, if I increase W by L also, right? If I will increase, I will get an increased GM, right? Now, what happens if I increase ID? If I increase ID, if I go to my circuit here, okay, that particular ID which is flowing here, when there is not that dissipates power, right? That is the actual power which we are taking from the power source, and that will continuously be generated as heat in this analog circuit, right? So that DC operating point, there will be some current which will be flowing continuously here, right? Unlike a digital circuit, and that will generate heat. So you will find that GM and ID is a trade-off. So you can get higher gain by increasing the ID. So which in turn means you will have to generate more heat and consume more power for higher gain. Similarly, if I increase W by L, okay, if I keep ID constant and just increase the width of this transistor out here, right? In that case, what happens? The area increases, okay, and also if the area increases and also the capacitance increases, and an increase in capacitance will adversely affect my high frequency operations. So these are the trade-offs which are there while computing GM and deciding the values of the currents and the size of the transistors. Is this okay to all of you? These are all very, very important aspects, okay, when you do practical designs. Is it clear to all of you?
Excuse me, sir.
Yeah, sure.
Sir, can you please go to the slide where you had few diagrams of the small signal equivalent?
Here.
Yeah. So here you said something about the marking. There was some issue with the marking, right?
Yeah, this should be small VGS, okay?
small VGS as in the sum of capital VGS
No,
as
no,
well as
no, no, small VGS, just the small
the
VGS,
net.
just the AC signal, it should be.
Just okay, fine.
Okay, okay.
Okay, thank you.
Okay, we will neglect this is alpha VDS in some, this is rarely used. Okay, alpha is nothing but an 1 by R0, so we will neglect this. Okay, we'll also have an R0 here. Okay, why is this R0 inserted? Here again from this graph you can see a small change in VDS, okay, will cause small change in ID, right? So we have to cater for that also. So that R0 also comes here, right? Now if I want to reduce this R0, okay, what is the things which I need to do? Okay, right? If I see
So,
the
sir, in that
R0, I have to increase the current, right? That is one way, or I can increase the length of the transistor. Okay, so these are some of the things we should know. R0, it is dependent on current. Higher current, it might give higher gain, but it might reduce R0. So these are all the things which you should keep in mind. Okay, generally it is in mega ohms and we don't bother about it, but then we'll see that R0 becomes an important issue when we are doing current mirrors and all. So it depends on the current, and also if you use large length of transistors, okay, if you keep L larger, but if you keep L larger, you have to keep the width also large for the same current values. So these are all trade-offs in analog design to achieve a target specifications. There will be a lot of computations. Okay, so you have to remember this also. Is it okay?
I think we need to decrease the length in order to increase R0.
No, we have to increase R0. We have to increase the length, because in large signals, in large channel, long devices, you have a negligible effect of VDS on the currents, right? So this is a problem with the short channel devices. So if you have to increase, okay, so that is that. Right?
So figure B and figure C are same?
They are the same. Only thing is this you can represent that same thing by an alpha VDS. Okay, the current source where alpha is an how this VDS reflects into a current. Okay, so a better option is R0. This is what most of the books follow. This is followed in so alpha is also is a function of R0 actually. Okay, you can convert this resistance into a current source, but this is not generally used. So we'll follow this convention. Okay.
Sir,
yeah, tell me.
So for all these analysis, we are assuming that MOSFET will be in saturation, na?
Yeah.
So for
we are assuming it's in saturation region. Okay. So now because GM we have from here we have started. This is a saturation region current. Okay. So for analog design, we'll generally try to bias the transistors in saturation region only. Okay. Yeah, tell me.
Yeah, I have one question. Like there you told like lambda is inversely proportional to L, right?
Yeah.
Somewhere. So in that way, R is the directly proportional to L, right?
Yes.
So if I need to decrease the R, then I need to decrease the length.
No, lambda is inversely proportional to
L, right? You have written in that diagram where you have saw that waveform.
No, okay, then there is a mistake which I have done here. Okay.
Okay. And second thing, sir, like here you told like if I increase the ID, then our power this picture only I was telling, right? So it's L is inversely proportional here, right? So if I substitute this value to here in R0, then L is the directly proportional to R0.
Yeah, so I might have made a mistake here.
Okay. And second thing you told like for GM, like if I want to increase the ID, so power dissipation will be increased, right?
Yeah.
And if I increase the width, then area will be increased, but R will be reduced, right? Then that
no, if I increase the width, okay, then my the capacitance will increase, which will adversely affect my high frequency operations.
Yeah, so if capacitance will be increased, so frequency switching will be more, right? Frequency will increase.
No, no.
Okay. So
yeah, it will create problems for high frequencies.
Okay.
Yeah. Okay. So where okay. Now we talked about R0, and also we said that if we change the base voltage, right? If the source is not at ground, okay, in that case the voltage between the source and the body also, when the signal is changing, like in this particular case, if I talk about here, the source is grounded, body is also grounded, but that may not be the case always, right? There could be this source may not be connected to the ground, and there could be some small signal which is appearing in the source also. In that case, okay, then I will have this signal GMB. Okay, GMB is the body, GMB, VBS. Okay, so this is a new component which is added out here. If I go to the small signal model here, GMB VGS. Okay, now we try to find out the value of GMB. What will be GMB? Like we found out what GM is.
One more thing.
Yeah.
Sir, in this A diagram itself, so when we were doing this derivation of GM on that page, we have derived the value of I capital D as this value. Here.
Yeah.
Right. So I capital D is the sum of the bias current plus the small signal current.
No, it is I capital D is only the bias current.
No, small I capital D in the next line. That figure, so in the second statement, in the second line of the equation, Here, this small I capital D, this is the sum of bias current as well as the drain, small signal current.
Yes. I do a differentiation, then this goes to 0. Then GM is actually small DID by small VGS. Is it
small
okay?
DID. So we are considering the capital I capital D to be 0.
Yeah. When I'm differentiating it, that is constant. So GM is actually D small ID by small.
That is a DC component, right?
This is a DC
component, and then it will after differentiation it will go to 0.
So,
right?
Okay, sir. So now if we go back to that diagram, that A part, over here this GM small VGS, this value is small I capital D or small I small d?
No, small I small d.
Small I small d. But should it not be the entire current which is flowing from drain to source?
No,
because capital I capital
small
D
signal equivalent, we just remove all the DC components. Okay, so just replace all this by small.
Adding to her question, if small I capital D denotes the GM capital V capital GS, then sir, I'm failing to understand here. If small I capital D is the total instantaneous value of current, and capital V capital GS gives me the DC component.
Just to avoid confusion, let's consider in this diagram everything as small. Does it sound okay?
Okay, sir. If
right,
is small, sir,
if this is all this ID, okay, this is capital ID, but nevertheless when I'm differentiating it, this goes, okay. So this actually GM is D small ID divided by small VGS, okay. So right, small I D delta of small ID divided by delta of small VGS, this particular GM. Right.
So sir, one thing I want to know. When we are expanding this small I capital D in the second statement, are we not mentioning plus ID component, or is it inclusive in this statement itself? And then due to differentiation, we are losing it.
See, either way you look at it, it doesn't matter, right? If I do delta of DID divided by small VGS, a small ID, I am looking at the change in the current when I am changing the small VGS. So this comes here, right?
Okay.
Right? I am interested in what is the change in the current happening, right? Is it okay?
Yes, sir.
Okay.
Sir, I have one question. Sir, when we are differentiating this red term with respect to small VGS,
yes.
So first term vanishes.
First vanishes, yes.
In the second, this 2 VGS minus VTN will be remaining.
Yes.
And 2 VGS will be there, right?
This we are assuming, since VGS is going to be very, very small, we are neglecting that.
Okay. So we are neglecting first and third term.
Yeah.
Okay, sir. Okay.
Okay. Right. Okay. Now we are talking about the. Okay. This is output conductance. Okay. This small value of R0. Okay. Which we got it as 1 by lambda VID. Okay. This is from the current equation, right? 1 plus lambda VDS. This is the current equation, right? We are differentiating it with respect to VDS. Okay. This goes, right? Only lambda remains. This is an approximately equal to ID. So I write it an ID. So I get the value of R0. So this is R0, right? So is this okay? Output conductance. This is also known as 1 by G0. Is it okay? Same thing, right? R0. Okay. Now the third thing which we inserted was this GMB. Okay. That.
Sir.
Yeah. Tell me.
Can you please come to the previous slide?
Yeah. Tell me.
Here besides the lambda, it is small VDS, right?
This one.
Yeah.
Yeah. Small VDS. Now we are talking about what happens when a small current change in voltage. VDS
okay.
It happens. Okay. So actually the DC R0 and small R0, they come out to be almost same, right? So there is no difference here, right? Now the same thing, this is the equation there. Now I have to find out this, right? Now we said by changing the bias voltage, the threshold voltage changes. Okay. Now the threshold voltage changes out here. So what I am doing is I am finding out dID divided by dVBS. Okay, that I am doing ID divided by VTN and VTN divided by VBS. Okay, I am doing the differentiation in 2 parts. And now VTN divided by VBS. So if you see here, I am just doing this part with respect to so this is the VTH equation, right? So if you do this differentiation, okay, with respect to the VSB, okay, and substitute here, so I get the value of an GM as this. Okay, so this is like right ID. I am doing it with respect to the backgate. So here VGS is not there is no VSB given in this directly equation. So I am first differentiating it with respect to VTN, and then I am differentiating VTN with respect to VSB. So that equation is given here. So if I do that differentiation in 2 steps, I will get the value of GM as this equation. Okay. So you can just I am sharing these slides. Okay, it is nothing, very, very simple thing which has been done, right? Here, because I want to find out the change in the current when I am changing VBS. So in this equation there is no VBS. So what is the thing which is going to vary here? Only VTN. So I am taking this as a variable and differentiating it once, and then again multiplying it by VTN divided by VBS. So I get that VBS, I am going to cater for that VBS also. So I am doing the differentiation in 2 parts. So I get the value of GM as this particular equation. Okay, so this is the value of GMB. Okay, so this is, but generally the value of the GMB will be given. Now if you see here, most of them are process parameters out here, right? It is dependent on GM. So for our at least for examination purpose, GM value will directly be given here. So you need to whenever we are replacing the MOSFET, So we are going to write this as GMBBS out here. Okay, so this is going to be the total small signal equivalent of this circuit. Okay, now for at high frequencies, okay, there will be some parasitic capacitances. I will talk about these capacitances in my VLSI class, but there will be some gate to source capacitance, gate to drain capacitance, gate to body capacitance, gate to substrate capacitance. So these are the additional capacitances which will come into the circuit. Each these capacitance we will discuss detail in our VLSI class. Okay, so just time being, just understand there will be some capacitances also, especially from gate to source and gate to drain. Okay, these two capacitances are very very important. Okay, they do play a huge role in analog design. So now let's first start with the design of a basic CS amplifier. How can a MOSFET be used to design an amplifier? Okay, so first I put we just discussed what is the purpose of these two resistances, right? So I put these two resistors here. I give a signal out here. So the small change of current voltage will be here. That small change of voltage will result in small change of current out here, right? That small change of current will cause a change of potential here, because that current is flowing through RD out here. We are assuming this load current is very very large out here. Okay, and what is the purpose of this capacitance out here? Anybody can you tell me?
For DC blocking?
Yeah, for DC blocking, because see, once we are operate, what should be the voltage out here, right? If I give 1.8 volt here, I want the maximum signal output here, so I'll keep it around 0.9 volt here. If I keep it as 0.9 volt, the signal can go from 0.9 to 1.8 and it can come to 0, right? So the for max swing conditions, this voltage has to be around 0.9 volt. Okay, but finally I just want an AC signal, so I put one capacitor here to block this signal here, right? So the purpose of these two resistances are understood. Now what is the purpose of this capacitors? Again, this is my small signal equivalent. So I don't want this DC voltage to go into this small signal, right? So I put a capacitor here to block this DC voltage going into the source. Okay, so this is a coupling capacitor which couples this small signal out here, right? So this resistance is very very important. Now what is the role of this resistance? And we will see. So this is how a common source amplifier looks like. Okay, so I have taken this screenshot from the LT Spice schematic, which I am going to simulate and show it to you also how it's going to perform, right? Now,
Sir,
yeah.
Why we are calling it as a common source?
Common source because this is gate, this is drain, and this is the source. Here in the input we are giving the signal between the gate and the source, and the output we are taking from the drain and the source. So the source is common to the input side as well as the output side. Okay, Abhishek, right?
Yes, sir. Yes, sir.
Yeah. Thanks a lot, because this is important to understand. So that is why it is known as common source. Is it understood why we are calling it common source?
Yes, sir. Yes, sir.
Okay. So that particular term.
And what?
Yeah.
Hi.
Yeah.
And why we are using R1 and R2?
R1 and R2 to bias this transistor. Right? If you don't give, it will be at 0 volt. Then the small signal 1 millivolt won't be enough to even trigger this transistor.
It means that we are giving some resistor divider voltage.
Yeah.
Then we ramping the input voltage, right?
Yeah, correct.
Okay.
Sir, as we know, MOSFET is an asymmetric device, and it can, like, depending on the potential, it can be source, drain, and all.
Correct.
So in that case, still it holds good calling the common source or common drain, and you'll be covering a common drain in a different topic, or
correct. Different topic.
Okay.
Right. This is common source. Okay. Once you do the DC biasing, the current is flowing in this direction. Okay. This is, once you have biased it, current will flow like this. Irrespective of the small signal, current will flow like this from top to bottom. It will increase or decrease, but the current direction will remain same or not? Is it going to remain the same? Large signal, right? That will be in few microamps. This small signal will be, it will be swinging from say 100 micro to 90 micro. but the current will always flow from top to bottom, right? That means current is flowing from, electrons will be flowing from bottom to top. So this is an NMOS. So the bottom one will remain as source always. Once we have done this kind of biasing, it continues to remain as a CS amplifier. Is it okay? Is it okay? Yeah, okay. So let me move forward. Right now, let's see how is that we are getting a gain. Okay. Now, if I call this voltage as VDD, right? This will be VDD minus IDRD. Correct? This voltage will be IDRD. Right? Now, V drain is equal to VDD minus IDC plus small id into RD. Okay, VDC. Now, if I open up this, okay, it will become VDD minus IDC RD. Okay, VDD minus IDC RD is the DC potential which is available here. So I call it as VDQ. Then the remaining will be minus ID RD. Is this equation clear to all of you? V drain is VDD minus ID RD. Okay, now I write this DC component plus AC component, right? Now I have removed this bracket and VDD minus IDC RD. Okay, that is the DC voltage which will be available here before application of the small signal. So that I am representing as VDQ, right? So now this becomes V drain, right? Now if I talk about this particular voltage, there is a capacitor which is put out here, right? So this DC component goes off. So I will get small id into RD, right? That is V out. And small id is GM into V in. Okay, small VGS. Small VGS is nothing but V in here. Okay, V in is when I call V in, it is always the small variation in the current V in. Okay, so I put this as V in here, right? So now this is V out, and V in is this. Right, so V out by V in is GM into RD. So this is the gain, right? So GM is mu is your this equation. For these typical values, okay, GM could be 1.4 milli, right? And RD, like here I have put 10K, so I can get a gain of around 14. So my small voltage signal will get amplified 14 times out here. Is it okay with all of you?
Sir, one question. When we actually, when RD is connected directly to V2, will we be still able to get, there will be huge power consumption here, right?
I see the power consumption out here in this circuit is, if ID is 1000 microampere, 1000 into 1.8, right? That power consumption, constant current will be flowing in this circuit. Isn't it?
Yes.
Right? So that is the power consumption we have. Okay, so that we can't have. This is not a digital circuit. So in analog circuits, there will be continuously power dissipation. Okay, so we get a gain of 14. Now if I want to increase the gain, what can I do? I can increase W by L, right? I can increase ID, right? I can increase RD also, right? Is it okay? How to increase the gain of an amplifier? Okay.
Sir, but increasing RD will decrease the current through it, no? Because inversely proportional.
Yeah, it is there, right? Now let me, if I have a given set of specifications, how to decide what R1 to put, what R2 to put, what RD to put, okay, what capacitance to put. Let's try and analyze that aspect. Right now,
one question.
Yeah, ask.
In that output equation, what does that minus negative sign indicates?
Yeah, sure. Thank you. Thank you, Sunil, for having brought out that question. Can anybody guess what does that negative signify?
180-degree phase shift in
the opposite direction.
Yeah, right. The output signal voltage will be inverted of the input signal. Okay. Why? I will tell you. See, if the input signal increases, okay, more current will increase, and if the current is increasing, then there will be more IR drop out here. So this voltage will go down. If the input voltage is decreasing, right, here current will decrease and lesser IR drop here, so this voltage will increase. So this negative signifies that the input and output voltage will be out of phase with each other. Is it okay, all of you?
Yeah, understood. Thanks.
Okay. So now coming to the small signal equivalent of if this circuit, okay, if I try to make, I can write GMVGS, right, R0. Here I didn't consider in this equation R0, but there will be an R0 also here, which is typically in few mega ohms, RD and RL also actually, okay, this RL also comes into parallel, right. When I talk about small signal of this circuit, okay, it is like superposition theorem. Okay, what do we do in the superposition theorem? We remove the voltage sources and put ground there, right? And right, if this is the source, okay, all the DC voltage we are going to put it as ground. All the capacitors we are going to short for the AC equivalent circuit. Okay, for the small signal circuit, whenever we make a small signal circuit, DC, so if there is a current source, we will see current source also later on. If there is a current source, we will leave it as open circuit, but if it is a voltage source, we short it. It is a simple superposition theorem, you can think it that way, right. So this is the small signal circuit, and what is this RG is? RG is actually parallel of R1 and R2. Okay, so I have put an RG here. Here we have assumed this source doesn't have a series resistance. So there is a series resistance also which has been put here. Okay, so from here to here it could be a potential divider, and there could be the entire V signal may not be available here. Some, okay, but if this is very, very large as compared to this, you can assume the total signal is available here, right? And then the gain becomes parallel of R0, RD and RL. And for common, this is one drawback of the common source amplifier, that RL should be much higher than RD. Okay. Otherwise, this can also affect the total gain. Is it okay till here? Is this small signal equivalent clear to all of you?
Yes, sir.
Yeah, okay. Now, let's try and find out the values of these resistance. Okay. So first,
sir,
yeah, tell me.
I have one doubt, sir.
Yeah.
So there are some rules regarding converting the transistor model to a small signal model, right?
Yeah.
Can you briefly explain once those rules?
No, this is the model. Okay, this is just VM VGS. Okay, all the DC sources will be grounded. DC voltage sources will be grounded. Okay, and current sources will be kept open, and capacitance will be shorted.
Okay, sir.
If there are inductors, that will be kept open.
Okay, sir.
Okay, capacitance short, inductor open, voltage sources short, and current sources open. Okay, okay. So now let's try and fix, okay, the values of these resistance. How to design an amplifier? Okay, so there will be some design constraints. First of all, there will be some max power constraint. Okay, we know it is better to keep ID as large as possible, because that will give me the desired gain. Okay, but then there might be a circuit, the total specification says ki I cannot exceed total power by this much amount. Okay, or the transistor itself, there might be a power restriction. So let's talk about the total net power requirement will which is specified will impose one restriction, that IQ into VDD should be less than max power constraint. Is this okay? First condition which I have to cater for. Okay. Now the second condition is known as slew rate. Okay. Now I want you all to just go through some literature on slew rate. Okay, slew rate is nothing but, see this output voltage, suppose this is driving one capacitance next stage. Okay, so how fast can it charge that node? Okay, that is dV0 divided by d max. Okay, so that is known as the slew rate. That slew rate is nothing but how fast this voltage can change with respect to the time. Okay, that depends on the load capacitance which is put here, right? If I put a large load capacitance, because this amplifier is going to, although I have put this as load resistance out here R, but generally in VLSI circuits this is going to drive next stage of amplifier, right? Some other CMOS devices. So there will be a C load which is available here. So greater the C load, it will take that much more time for this output to get charged or discharged. So that max rate of charge, okay, output change is defined as a slew rate, right? So now if I want this output signal, okay, to go at a fast rate, okay, I should have a large ID, right? So the slew rate is defined as I d cube divided by C load. Okay, this is very simple derivation. You can just try to you Google what is slew rate. You will get this equation. Okay, and how to go about. Okay, understood this slew rate. Suppose I have a slew rate requirement of 1 millivolt per second, right? So if I have to meet that slew rate requirement, okay, I can't just tell you to make a design with slew rate this much without giving the C load. I have to give you C load also. For this particular capacitance load, I require this much slew rate. So accordingly, I have to put in adequate DC current. Okay. So this equation will set the minimum IQ requirement. This will set the maximum IQ requirement. Is it okay with all of you?
Sir, but
yeah,
if we want like optimum slew rate, the R load should be minimum, right? Is the understanding correct?
No, we are talking about R naught is, if it is not there, if it is as high as possible, it is better, because that much current from the source will be diverted outside. If you have an R naught load, that much current will get consumed here. So R naught is always as high as possible is better.
Oh, okay.
Right? Okay.
Yeah, thank you.
Okay. So the DC operating current, if I have a large current flowing in this branch, that will help me that much current. So slew rate is directly proportional to IDQ. Okay. It depends on C load also. So now slew rate will define minimum IDQ, and the max power will decide the max IDQ. So I will accordingly take one IDQ which is in between these two. Is it okay with all of you? Is it okay? Yeah.
Yes, sir. The C load is different than C2, right? C load will be in parallel to R load.
Yeah. R load. It will be in parallel to R load. C load is different. Okay. So once the current is decided, okay, we fix the current. Okay, whether it could be 100 micro or 200 micro, depending on the user specifications. I have fixed the current. Now comes what should be the value of RD. Okay. Now I want what should be the ideal voltage here. It is 1.8 volt. So I should have 0.9 volt here, so that when the signal is swinging, it can go to 1.8, and when the signal is dropping, it can go to 0. So ideally I should keep it as a 0.9 volt here, DC operating condition, for max symmetrical output swing. Okay. So with that, I can compute the value of RD to be a VDD divided by 2 IDQ. VDD by 2 by IDQ. So I know how to fix the value of RD now. Is it clear to all of you now?
Yes, sir.
Okay. Now I fix the value of RD. Now let me go back. Now what about this transistor? Now I know gain is minus GM into RD. RD has got fixed, right? Gain will be again given by the user. Okay, he says I want 14, gain of 14. I want gain of 15, whatever he says. Okay, so now this is the GM equation. Here ID is fixed. Now W by L, will it get fixed now?
Sir, actually, what is the difference between ID and IDQ?
IDQ is the it's the same, capital ID, this ID.
Both are same.
Operating, Q means operating point. Okay. Okay. Now since ID is fixed, okay, gain is given by the user. Can I fix W by L?
Yes, sir.
Yeah. Okay.
Yes, sir.
Okay. Now I know the value of RD. I know what is this transistor size. Okay. Yeah, tell me, somebody has got any doubt?
Sir, here in point 2, when we are finding the maximum symmetrical output swing,
Uh-huh.
so here we are assuming that the swing voltage at drain can be from 0 to VDD.
Yeah.
Shouldn't it be from V overdrive to VDD for a transistor to remain in saturation region?
No. For this saturation, you can do that also. You want to remove this, but generally we don't go to that extremes, right? So we generally take it as VDD by 2. Okay, this is hand calculation, right? This is just a hand calculation how to design these circuits. Okay. Okay. Yeah, tell me.
Slow rate will depend on load current, right? Why you are depending on IDQ?
On the load
current, right?
Yeah. See, so the current which will go into.
But you mentioned it as a IDQ, right?
Yeah. Load current is that IDQ only will be diverted towards the load.
Okay.
That only will go to the load, or it will come from the load. Okay. Charging, discharging of that capacitance will be driven by IDQ only. Okay. So,
sir, IDQ is a DC current, correct?
Correct.
So it will not be diverted to load.
No. That, see, IDQ instead of flowing here, it can go into the capacitor or it can come to the capacitor. Okay. So the DC operating current only will is the one which defines which is the max. So this derivation is there. You can just Google it. In case you have difficulties, I can get into the derivation of this also. Okay. Just find out sleeve rate. I'll keep leaving small things in between so that you do your little bit of homework also. Okay. Okay. So now I have decided the value of W by L. Now I want an R1 and R2. Okay. Now from this equation, can I find out now ID from this ID equation, right? ID is equal to, you have that particular big equation, right? From there, can I find out V overdrive? ID is fixed, W by L is fixed, right? So V overdrive, from the normal ID equation, I can find V overdrive, right? So I can find V overdrive. Once W by L is fixed, ID is fixed. Now V overdrive, VGS minus VTH can be found out. Once VGS overdrive is found out, you can find out VGS also. That is overdrive plus VTH, right? That voltage. Okay, if that voltage is found out, then I can use the potential divider here to get that voltage out here. That's how I can fix the value of R1 and R2. Is it okay with all of you? How to get R1 and R2?
Yes, sir.
Okay. Yes. Yeah. Okay. Okay. Now I can have this 7.5K and 3K, right? I can have 750 and 300K. So what would be the advantages, disadvantages? Can you think of something?
The current drawn.
Yeah, see, if you see the current which is flowing here, okay, that is waste, right? I just require a potential divider here, right? So if I put 7 ohms and 3 ohms, large current will flow here. It is of no use. Then why not put mega ohm and mega ohm here? Okay, mega ohm and mega ohm will cause two particular problems. Okay, the first problem is
size and heat.
The first problem is size, like you said. Okay. Okay. Then now since you brought one more aspect, there are three different problems. Okay, first is size, second is noise. Okay, when we do the noise modeling of resistors, larger resistance means larger noise. Okay, so it may not for RF applications for and all, noise becomes a big issue. Okay, so one is size, one is noise. The third issue is, now if you see, I have a small signal here. This is a capacitance, this is a resistance. Okay, so this is like an what? It's a low pass filter or a high pass filter?
High pass.
High pass filter, right? So if I use a large resistance, like if I use a large resistance, the capacitance also needs to be put large. Correct?
Yes.
Correct. So that will increase the size of the
low pass, high pass filter, sir.
High pass filter only. That's what I'm doing. It's an high pass filter. So if you increase the value of the resistance, this also needs to be increased. So moderately, the 75, 30K, this is the range of resistance which I can use. Okay, so this no hard and fast rule. You can use it in the mega ohms also. So accordingly, you need to now what is the value of these two capacitances? Okay, now these capacitors depends on your frequency of operation. So since we already said this is an high pass capacitance, so if I am using it for 1 kilohertz application, then this has to be at least RC value. Omega is equal to 1 by RC, right? Right? For low pass filter, at least 1 decade frequency lower it should cater. So the value of the capacitance will be decided based on the frequency of operation. Is it okay?
Sir?
Yes, sir.
Hello?
Right?
Sir, why you are saying if R is more, C must be more?
Because for a given frequency, if it has to pass, right, for this low pass filter, okay, the frequency, the minimum frequency which it will pass will be 1 by RC, right? Omega is equal to 1 by RC or 1 by root RC it is.
Oh, it is fine, but why you are saying if R is more, C1 must be increased like that? The product must be increased or decreased, right, based upon input frequency?
Pardon?
The product RC must be increased or decreased based upon the input frequency. So it not be like that if R is more, C must be more like that, right?
Yeah. Correct. Okay, I stand corrected on that aspect. Right. So the value of the these two C, this C also will work in conjunction with these resistors. So they will also become a filter. This will also become a filter. So these filters have to cater for the frequency given by this filter and by this filter. Right. Suppose I am giving 1 kilohertz signal. Okay. So 1 decade lower. That means this will R1 be parallel to R2. Okay. When we talk about filter, you should because this is a small signal circuit, I will consider R1 parallel to R2. Okay. So that resistance which is coming plus this capacitance. Okay. That will be a high pass filter, and that cutoff frequency, if I am talking about 1 kilohertz, the cutoff frequency of this filter should be 1 kilohertz divided by 10, that is 100 hertz. Okay, so that this 1 kilohertz can smoothly follow. So that is the design criteria which I am going to use. Is this aspect clear to you? What I am talking about? Is it okay with all of you?
So sir, we have to take care resistor and capacitor value together.
Yeah.
We can't.
No, first you decide the value of the resistors, okay, and then you compute the value of the capacitance in such a manner that, okay, at least 1 decade lower frequency is the pole which is given by this circuit.
Correct.
Okay, same holds here also, this capacitance and this resistance. Okay, so you need to take care of that aspect. Okay. So now we can do this load analysis using this thing also, using a diagram also out here. This is VDS, okay. This is the various VGS, okay. So I can plot one line out here once RD is fixed, okay. So I put this point as VDD divided by RD, and I put this as VDS. I draw a line out here. Okay, so graphical point here. Okay, and then I can decide from this graph once an ID is fixed. Okay, the value of an VDS. So graphically also what we did in here mathematically, if you want to do it in graphically also, we can do that by drawing these graphs. Okay, and all these conditions, and we know we can decide this as an operating point, this as an operating point, this as an operating point. So accordingly we can do this. Okay, so but this is generally we do hand calculations only, so that gives us, but otherwise if somebody is interested in doing something based on this, you can do that also. Okay, so this is
Sir, can we get 5-minute break?
please.
Yeah, okay, sure. Yeah, we'll take a break out here.
Sir, source of this content is Cedra Smith?
Yeah, this is from Cedra Smith.
Okay.
So it is in a 43, 48. Now we'll assemble back.
Sorry?
It is now 1444. So 1449 we will assemble back.
Okay.
Hi, sir. Meanwhile, in the break, I want to discuss something. Like there were. Hello.
Yeah. Tell me.
Yeah, there were chats. I mean, there were groups created in the chat. There was one group where it said analog IC design, right, where you upload the videos and all. Sir, I'm not able to access that chat. I mean, I'm no longer a participant. It's showing that.
Which chat?
Analog IC design in the team.
In the team, is it?
Yeah.
See, you need to get into the back. Put a mail to the backend team. Okay, you can give me a copy of that also.
Okay, shall I send you in the personal mail or in the team communications?
You send a personal mail and I'll have a look at it. If you can.
Okay, sure.
Okay.
So,
if I can add you as a participant, I'll do it myself. But I think it is better that they do it, because I don't know if I add whether you will get the entire communication or not. It is better they do it. Yeah. Tell me.
Oh,
sir. Hello, sir.
Yeah, tell me.
As far as mid semester and final semesters are concerned, regarding the questions, sir, do we need to keep subjective and quantitative approach both, or is it only quantitative?
It will be
questions
questions will be only numericals.
Okay, sir.
Because it is open book.
Hello.
Yeah, tell me.
Sir, in the GM equation, in the last you got that ID, right? Root the formula, that DC ID. So can you explain that ID, how we got that? One small doubt.
Here?
Yes, sir. This one.
See, what is this? GM mu and stock, this, right? So what is VGS minus VTM? Neglect this effort. This. Okay, 1 plus lambda VDS neglect. This is a root of ID divided by this, right?
Okay.
Okay, you put that, right? Here, so this will, this is in the denominator, okay? So this now becomes inside the numerator. This becomes ID out here, right?
Okay.
And we can add one more equation for GM. GM equals to 2ID by overdrive voltage.
Yeah, you can do that also.
Yeah.
Yeah, sir, are these lectures available on your website as well?
No, this course I am taking it for the first time. So today's lecture I am recording it. I'll put it there. I'll be uploading all these PDFs and there. Yeah, okay, shall we start now? If I have to summarize, okay, about CS amplifier, these points are very important, okay. What the gain is a function of load resistance, right? So suppose I have, like, if you have an earphone, right, which is only 4 ohms, 5 ohms, will these kind of amplifiers, is this good enough? It is not, right? Because if I have RL is equal to 4 ohms, 5 ohms, the entire gain will be lost. Okay. So it is a function of load resistance, that is, it has got high input impedance, right? Because this is gate, this is open. So the input impedance is very, very high. Okay. So this is beneficial in some cases. But if I talk about RF amplifiers, where suppose I am connecting an antenna which is only 50 ohms, in that case I cannot connect that antenna to the CS amplifier, right? Because there will be a mismatch of the impedance. Okay, they are all low impedance sources. So in that case there will be lot of reflections. So this is not ideal for those kind of applications where the input source impedance is low. Okay, so high input impedance is when one amplifier is driving this amplifier within a VLSI circuit, this is fine. Okay, high input impedance is an advantage. Okay, the third one is it has got an issue with a high Miller capacitance. Okay, so that restricts this its operation at high frequencies. Okay, so let me explain you what an high Miller capacitance is. You can go through your BTech. I think in a Millman-Hall case. Okay, this is this derivation is given there. You have a V in. If you have an amplifier and if you have an capacitance which connects the input to the output like this, right? Then this is the equivalent circuit. Okay, this is the effective capacitance now will be 1 minus A. Okay, minus A is the gain. Okay. In this particular case, for a CS amplifier, from here to here there is gain, right? And that is negative. Okay, so this minus becomes plus, and then so this gate to drain capacitance gets and this is the gain GM into RL dash. R dash is the net load resistance. Okay, so if you put here, so you will find that this equivalent capacitance is very, very, very large out here, right? If you have a large capacitance, what happens to the small signal? It will die down here, right? So it will act like an low pass filter, right? So high frequencies will get shorted. So this imposes an limitations on high frequency applications. Okay, is it understood why this is not suited? This particular thing is not suited for high frequency applications. Basically, you have gate to drain voltage. Okay, capacitance, which has, since the signal is getting amplified from here to here. Okay, it becomes an C equivalent, which is multiplied by the gain. Okay, approximately multiplied by the gain. So you have a huge capacitance here, which puts in restrictions on its high frequency application. Is it okay with all of you?
Yeah. What is the range of frequency?
No.
We can use this CS amplifier.
It depends on your actually the kind of MOSFETs you are using, the technology. W by L, right? A few megahertz will not be a problem. Gigahertz, it could hurt you. Okay, we can do that simulation and find out. Okay, right. Okay. Now, if you see here, what is the problem with giving a gate voltage out here like this is a small variation in VDD will cause variation in gate voltage, right? Because if you are biasing it like this, a small variation of VDD will cause variation in voltage here, right? And also what will happen because this and that will cause, because if you see ID VGS curve, it is like this, right? So a small VDD variation will cause this Q point from changing a lot, right? So this is not an it is known as Q point stability is very, very low in this particular case. If you see here ID, right, it is square of VGS minus VTS, right? So this bias voltage, okay, it becomes very, very immune to VDD variations, right? Because in a circuit you have to cater for that VDD variations also. So this biasing stability is not there for particular for the CS amplifier. So we need to modify this circuit a bit. And now what I am going to do is, there is another amplifier which is known as CS stage with source degeneration. Okay, so I have put one more source resistance here. Right now, if I put one more source resistance here, now this is V in is equal to VGS plus IDRS. Now if I write in a delta ID, okay, delta V in minus delta VGS by RS. So now any change in V in or VGS, okay, because of the change in power supply voltage, will you have an RS in the denominator. That is why ID will not vary that much. Is it understood? ID gets stabilized a lot. Is it okay with all of you? Yeah, Shiva, Ayush, anybody?
I have a question.
Yeah, ask me.
This RS is not the replacement of the bias voltage which we generated R1 bias.
That will
right?
be there. That will be there.
Yes.
Over and above that, I am putting one RS.
Yes. Yeah. This is the ripple we get from the VDD. We can control from this source degeneration.
Correct.
Right.
Correct.
The other path still it is existing between the R1, R2 and VDD. Right.
Yeah, that will be there.
Okay. Thank you.
Okay. So now I have put one RS. Now what happens if I put this RS? What happens to the gain? Right now the input small signal becomes V in is equal to VGS plus ID RS. Now V in and VGS are not the same. I have one because V in is here, VGS is here, and RS is also there. So I have this additional component coming here. Right now ID I replace by GM VGS. I take VGS common. Right, it becomes 1 plus GM RS. Right. Okay. Now V out is ID RD. Okay, like it was in the previous case it is. So now if I take the gain, it will become RD divided by RS. RD divided by RS. Okay. So this is the gain. Now if you see here, by putting an RS, my gain reduces. Okay. My gain reduces a lot. So this is not a very desirable thing. Although my bias stability has increased, my gain has reduced. Okay. So that is one drawback. Okay. Now how to get back the gain to the previous value. Okay.
Excuse me, sir. Can you please repeat how we got rid of the ripples once again? The purpose of RS.
RS. Okay. Now if you see, this is V in. Okay. VGS plus ID RS. Right. So I write delta ID as delta V in minus VGS divided by RS. Okay. So the ripples voltage, right? This R1 and R2 is there. Here R1 R2. So the supply change voltage, ripple in the voltages here, supply voltages will result in delta V in, right? So initially delta V in here, delta V in was causing an ID. It was rated as square of ID. So there was lot of variation. Here in this case, delta V in, if you see here, what is happening? It is getting divided by RS, and that is why the ripple effect is lesser. Is it okay?
Yes, sir. Thank you.
Okay. So now the gain is reduced. Now to get back the gain, what I do is I put one capacitor here, right? Now this value, this capacitor, what it does is, for DC analysis, all these 4 resistance are there. For AC analysis, this is not there. Correct? So I get back the gain as GMRD. Is it okay with all of you? Okay. So this is how a CS amplifier, actual CS amplifier looks like. There will be an RS to stabilize the DC operating point. This capacitance will bypass this. Okay. Now since I have put RD, now how to go about finding out the values of this R1, R2, RS, RD. The first ID, these two conditions, they remain the same. Okay. Then to find out RD. Okay. Now we will assume that, okay, this is all hand calculations. Okay. We will allow 10% of VDD to be dropped across RS. Okay. If I am allowing 10% of VDD to be dropped across these things, then it will be 0.9 VDD divided by 2 into divided by IQ. So this is how I fix the value of RD, because I am allowing 10% of VDD across RS. Is it okay? These are hand calculations. Okay, how to go about designing your practical circuits. Okay, these steps may not be given in your textbooks. Okay, I am giving this you this will be available only in practical design literature for your if you are working in the industry, then it will help. Okay, these are all how we go about doing calculations. Okay, this may not be there in our standard textbooks. Okay, these equations. Okay, Is it okay? How did we get RD? Yeah. Anybody? Can you just?
Yes, sir.
Okay. Now RS is also.
What is the need of 0.9 here?
That's what I said.
We are doing VDD by 2.
Right. We are allowing 10% voltage drop across RS. So now that is hand calculation. Okay. So the RS we will compute by 0.9 VDD by IDQ. Okay. Rest of the calculations are same as that of the previous design. Okay. So these are the two variations which come in. Okay. Now this combination of RS should be like if my operating signal is 1 kilohertz, this RS should bypass even 100 hertz. Okay. If it is 1 megahertz, then 1 megahertz 100 kilohertz. Okay. This RS combination should come like that. Is it okay? This RS combination should, these R1 R2 in parallel in combination with this C should cater for, and if it is 1 megahertz, 100 kilohertz, like at least 1 decade it should cater for. Okay, all these poles which are formed. So you have to decide the value of the capacitance accordingly, right? Okay. Now we still have some time. Okay. Now we can also bias this transistor. We can use, instead of RD, constant current supply source. Okay. So in that case, okay, this, if I go for a small signal equivalent circuit, this will be open circuit and the gain will be given by GM into R0. Okay, so that is the maximum. So graphically we will fix the ID like this, right? Okay, so we can have a constant supply also, constant current source. And how to design this constant current source? What I can do is, okay, this is the R0 parallel to ROC. This constant, if I take a non-ideal current source, then this will be the resistance of the of that non-ideal current source. Okay, why? So this is one way of designing with constant and current supply source. Okay, so if this current source is made independent of temperature and things like that, then you are it will be more stable with respect to the operating point. Okay, so you just have to give some voltage out here, but that voltage variation will not cause ID variation because you are supplying constant current in this path. Okay, so I'll explain you how this is given in the next few slides. Okay, that is one option. You can also make CS amplifier with Pmos. Okay, so this is the constant current source or RD, what we called. Okay, that has come in the bottom, and you can use an Pmos also. So we can have an Pmos channel CS amplifier also. Okay, same way. So this will be the equivalent circuit. So I'll share this PDF. Just try to analyze this, how Pmos works. It is exactly works in the same manner. Okay. Now this is the constant current source circuit. Okay. This is our main transistor out here. Here, like, this is I reference. What is I reference is this is an reference current which is independent of VDD variations and it is independent of temperature variations. Okay, so those kind of reference currents will be generated. Okay, so in all your analog circuits we have something known as band gap reference circuits, which is not part of your syllabus, but then if I find some spare time, I will try and explain you how those circuits work. So we generate reference currents which are independent of VDD and independent of temperature. Okay, now that current is flowing in this particular one current through this Pmos, and if you connect this as a current mirror, the same current will flow here. So if this is 10 micro, if you adjust the width of these two transistors, okay, if I put 1 micro, the same current will flow here. If I put 1 micro and 10 micro here, 10 microamperes current will flow here. Okay, so that current which is used for biasing of this transistor will be independent of temperature and VDD variations. Okay, you just have to give some VGS value here to cater for that current. Okay, but that current will, even if that varies, this current will remain constant. Okay, so this is known as current amplifier with active loads, right? So this is the equivalent circuit. Okay. Now if I look into this M2 transistor, it will be R02. Okay. So the gain will be Gm into Vn, R01 parallel to R02. So this is the equivalent circuit. So after this I will show you some demonstration which will make things more clear. Is this equivalent circuit and the operation of this circuit clear to all of you? More about current mirrors we will talk after 2-3 classes, but a time being, just understand we are generating a reference current which is independent of VDD and current, and then we are passing that current, constant current into this so that the biasing condition doesn't change. So this is the kind of circuits which is actually employed in all VLSI designs. Okay, we don't generally use even this circuit. Okay, more stable circuit is this for using biasing. Obviously you will require R1 and R2 so that if this VGS is higher, it is good enough to support this current, that's all. But that will not decide the current. The current will be decided by these two transistors and this I reference. Is this much clear to all of you? Anybody has got any doubts? Yeah, tell me.
So this active load is used just for the stability purpose, or is there any other purposes for using this active load like this current mirror circuits?
Yeah, there are other issues, other advantages also. Firstly, see, RD imposes a lot of constraints actually, right? RD, it is like RD to set the current, you have to have an higher RD there, right? And that if you see the design where we studied, other than stability, okay, it is easy to use an Pmos and get the desired voltage here, right? Rather than, because if you use an and the gain R0 will be very, very high first of all, right? Here if I use high RD, then the current will drop, right? But that doesn't happen in case of an Pmos. Pmos can give high current while keeping R0 also very high, right? Because the output resistance is very high, right? But it can support currents also. In this case, if I have to support high currents, okay, and maintain the gain, then this voltage operating point will come down drastically. So this gives larger flexibility in the design. When you design with active current load, this gives a larger flexibility. Is it okay?
Sir, I have one question.
Yes, sir.
Yeah, tell me.
Sir, earlier we were having RD as a resistor. So it was in parallel with the R0 of M1.
Yeah.
So since R0 of M1 was very high, we were able to ignore this, and RD was the resultant, right? GMRD was the gain.
Correct.
But if we are using active load, there M2 for the Pmos R0 is very high, and also for NMOS R0 is very high. So
correct.
When we are taking parallel, the result will be very less, right?
No, both are very high. So R0 will be very high. Okay, 10 mega ohm, 10 mega ohm will give you say 5 mega ohms. So you will get higher gain.
Okay.
Right. So that is the flexibility. It will give higher by using active gain. Your R will be very high. Okay, so you will get higher gains in this case. Right. The gain will be higher, and to set the operating point also it will be easier. Correct? Okay.
Yes, sir.
How to set the operating point? Just think over it. I can see this is a Pmos, right? Once we decide what is the current, okay, how to set W by L? Just use the ID equation, right? And set the W by L of this transistor so that this ID follows here. Okay, VDS is known, so we can set the ID equation. Right, so if you keep exactly the same size of these transistors, right? If you keep half the size of the width of this transistor, you will approximately get VDD by 2, because Pmos has got almost double the resistance. If the same current is flowing here, right, and if I keep the width of this M1, M2 double that of M1, generally we will get VDD by 2 here. Is my statement then very important? Understood? Because mu p is almost half of mu n. If I keep the width of this transistor, okay, double as that of this, I will get VDD by 2 here. Is it okay?
Yes, sir.
Okay, so these are okay. Okay, see, see, there's a lot of things to learn, right? And the entire single stage design is one lecture as per your course handout, but I am going to cover it in 2 lectures. In spite of that, I will not be able to cover full detail. So I will try and give as much as possible, but I will request all of you to go through the Razavi's textbooks properly. Okay, most of the important points I will cover, but then still. Okay, so this is the you might get some assignments like this. Okay, so this is like a 10K AC signal I have given here. Okay, so this is the AC signal. So if you see here, AC this is a 1 millivolt signal I am giving here. Okay, 1 millivolt. Now once I go to source voltage here, if I go to here, okay, if I take an you can go through my videos, you will get. Okay, you right click here, advanced sinusoidal signal. Okay, so a DC offset amplitude and all these parameters will come. So I have taken 1 millivolt signal, 1 kilohertz here signal out here. I have put these resistances what we discussed in the class, and I am doing a simulation. Sorry, I am doing a transient simulation. Right, so this is the AC 1 millivolt signal which I am getting here. If I plot the output, see, so this is the output around 12 millivolt signal. Okay, so this is how the signal is amplified, right? So if I plot it here, this signal, so this has got a DC component. So let me cut this source voltage and V out. So it is around close to 0.9 volt. This is around close to 0.9 volt. It is going from 960 millivolt to 986. So this is the voltage which is available here, right? Now if I want to improve the gain, what can I do? Can somebody tell me? Can I increase this resistance? Right? If I put it into, instead of 10K, if I put it as 20K and run it, right? Now if you see here, the gain has slightly gone higher, right? But then it has changed the DC operating point also, right? So this is how. So you can change this value of the resistance to change the gain, but it will change the DC operating point, right? Similarly, I can this is 25 micro. If I put it into just 10 micro, and if I run this, let me close this. Initially I was getting a gain of 12. Now I have reduced the size. So if I take the V output, now it is 6 millivolt to 6 millivolt, right? This output 1 millivolt, I am getting gain of only 6 because I have reduced the size of this. If I go back and I put it as 20, okay, if I run, now it is around 10 to 10, right? So the gain has gone high. So you know, all these things which we have discussed, all these things is visible out here, right? Now I said one of the drawbacks of this circuit is I cannot use it for low load. So if I put, instead of 100K, if I just put 100, okay, and if I run it, so if you see here, the gain is only in microvolts, right? So the entire, because GM into, now we assumed that this has to be very high, right? Now if I am putting just 100, now I am not getting any gain out here. Okay, so these kind of simulations, and once you get familiar with LT Spice, you should do it yourself. So let me revert back this to 100K. Okay, So these were the things, and I can also, this is known as the transient analysis. Okay, now let me disable this transient analysis. Okay.
Sir,
yeah.
Hello. Sir, can you show the output again, by probing it before C2?
Okay. 10 millivolt. Here. Before C2. This is 1.1 is the DC operating point. So
1.1, okay.
Right. See, it's
okay.
moving.
So waveform come at 1.1 volt with AC response.
Correct.
Okay.
Right? Is it okay? Okay. Now I can also do an transient analysis. No, AC analysis. Okay. Now what I do is let me disable this. So let me remove this dot, so it will become okay, and let me put a comma there instead. Okay. So this tran as well. Let me do an AC analysis. I am doing an AC analysis and I am plotting the output. Okay. Now, if you see, this is the AC. So the gain is around 19 dB out. Like here, because the input I have put as amplitude as 1. Okay. That 1 is AC amplitude. Okay. The actual amplitude is 1 millivolt. Okay. This is an AC amplitude. So this output is actually 19 dB. So you can say it is 19 dB gain out here, right? And at around 100 megahertz, after 100 megahertz, somewhere here, okay, it is started dropping. Okay, why is this drop? Can anybody say? Yeah, it is not because of this capacitor, because of the Miller capacitance. Okay, is it okay?
Yes.
Okay. Now suppose I don't use a large capacitance here. Okay, I just use 1 micro, right? If I run, okay, then you see here the problem comes here, right? Is it visible, the problem here? Right? It can handle only 100 hertz and above because this capacitance is low. Is it okay? Now if I put this as just a 1 nano and I run it, you see here about 10 kilohertz. So you understand the importance of this, the other capacitance here. Is it okay with all of you? Right?
Yes, sir. Yes, sir.
Okay.
Sir, can you explain?
Yeah, tell me.
So, I don't get
this capacitance, is it? I told this RC value, okay, this is a high pass filter. This has to be large enough to allow our desired frequencies. Right? If you keep this capacitance low, it is going to attenuate the low signals. Is it okay?
So it's a high pass filter, so definitely it will attenuate the low frequency.
Yeah, so if I have to move this towards the left, I have to use higher capacitance, that's all. Right?
Okay.
So the value of the capacitance should be decided accordingly. So everything about an CMOS, is it CS amplifier, is it clear? How to get gain, how to do the biasing. So if I plot the signal out here, okay, let me do an.
In the previous plot, when the output and the high frequency component got attenuated, not in this plot, where you were saying it from Miller.
No, here also it is getting attenuated. Here you can just because this it is there, it is not clearly showing. It is there here also.
This attenuation is it C2 will also contribute the coupling capacitor on the output.
No, this C2 also will contribute towards the low frequency only. High frequency will be contributed by the CGD essentially.
Yes.
Okay. Is it okay?
Can we see that capacitance value, CGD value?
No, actually, in this particular software, it will not. In Cadence, you can find out what is the value of CGD. It will give the here you can open up the .lib file, right? If you open up the .lib file as a text document, okay, open it up in Note, then you will get all the equations which have been used for this transistor. Okay. So let me quickly show you a few more simulations before the time gets over, because I got an one more class followed by this. Okay. So I can have a Pmos amplifier also, similar thing. I have put R here instead of on top. I have put it here, right? So I ran the simulation. This is a 1 millivolt output. Now see, now this is almost 12 millivolt. So using Pmos also I can make an amplifier. Okay, similar thing. I can also have CS plus RS amplifier. I told we are going to put one more RS out here, right? So if I do a simulation, Vs and V out, okay, I can get the same gain because I have put RS, but I have put one capacitor also in parallel. So that is why I am getting the full gain here. So I have slightly adjusted the values of these resistances out here. This is 20k and 2k, so that I have around some voltage out here also, some voltage out here also, right? Now suppose, so this is giving me a gain of almost 14, right? Now suppose I cut this capacitor out here, right, and do the run. Now if you see here, this is like 1 to 1, peak to peak is 2, and whereas this peak to peak is around 10, so around 5 times the gain. So RS divided by R3, right, 10. So you will find okay, whereas here it is 2 and 10, 5. So there obviously we were talking about we had neglected few things in the model. So it is giving slightly lesser than, but it should give 10 theoretically like this. Okay, that we found out RD divided by RS was an approximate value, right? Not considering R0 and other effects. Okay, so you will find that gain is reduced significantly on removing this capacitance. So if I put back this capacitance and if I run it, I will get a large gain. Okay. Is these things clear to all of you?
Yeah, sir. Which one is recommended, the NMOS one or the PMOS one? As we know, like when the so basically both PMOS and NMOS having a same driving strength at the lower node. So will it make any difference over PMOS and NMOS?
Doesn't make much a difference, right?
Okay. So and on the higher technology, right, like 180 and all. So to get like if to proper inverter, right, you used to have a 2:1 or 3:1 ratio between N and PMOS. In that case, NMOS will be a better choice over the PMOS, right?
You're talking about digital design or analog?
Oh, okay. Yeah, analog. Yeah.
It doesn't matter. See, everything has PMOS has gotten a slightly greater R0, but then it might have for the same current you might have to use slightly larger transistor because of mu P being lower than mu N. So if you do that might affect the mobility, right? In digital design it is simple. Okay, area, power, delay, right? For analog design there are so many things which come in picture, right? So you have to
So one more thing, we have not talked about this output voltage swing here, right?
Output voltage
swing. I mean, to keep the transistor in saturation region, V out is limited, max V out. Or
yeah, we designed it that way, right? If you keep increasing, we have kept it somewhere in between here. If you keep increasing Vs, after some time, okay, it will touch the saturation levels.
Yes, yes.
Okay. So this is the constant current source circuit. If you see, this is a constant current source. This is an PMOS. I run this, Okay, let me plot the current. Okay, the current out here is okay, this is the voltage which has got the current. Okay, the current out here is okay. Okay, now I have to put a marker there. Okay, it is around 19 micro, but I have placed this as 10 micro and I place this as 100 micro. Okay, so that 10 times the current flows here. Now if I try to plot the current which is flowing here, right now it is around 200 microampere. Okay, less than 2. So so you find, so let me plot Vs and V out, right? So this is Vs. Okay, this is V out. So I am getting a much higher gains here, like it is from 25 to 25. Okay, I am getting much higher gain as compared to that CS amplifier, because R0 is very high here. Okay, as compared to RD. Right, so I am getting higher gains out here. See, the gains are 25 and 25, right? Minus 25 to 25. There we got around 10 or 14. Here I am getting with a constant current bias, because the resistance is RD value. Right, instead of RD it has got replaced by R0, which is typically in mega ohms. So I am getting a much higher gain out here. Is this okay with all of you?
I have one. Yeah, this one I understood. V out, we have a load capacitance, right? Consider something like a C4. If add C4, another 1000 micron or 2000 microfarad capacitance, this will reduce our GM, right? Our output swing.
Yeah, it will reduce the gain.
Right? Okay.
But generally, generally the gate capacitances, if it is driving another MOSFET gate, okay, the gate capacitance are of the order of few femtofarads, 10 to the power of minus, right? So they don't really.
In that case, that way we are ignoring.
Yeah, it will. You can ignore that, because MOSFET gate capacitance will be 10 to the power of minus 15. Okay, this we are talking about minus 6 and all. So you can actually. So that is why we are more concentrated about load and resistance, what it is going to do. Okay. So
understood. Thank you.
So I think what parallelly what you should try and do is I'll share all these videos, but then what you should try and implement all these circuits of your own, right? So slowly in your once you get used to your LT spice. Okay, so for the analog design, all the circuits which I have demonstrated, you should be able to make it yourself also. In case you are getting stuck, please let me know. Okay, so let us now call this off today. Thanks a lot. Because I have a class. Yeah, tell me.
Here to find the operating DC voltage, that is 1.3 volts. That will be V3 minus. That will be V3 minus 100 micro into R naught of M2, is it?
This voltage, right? Okay, that this will be actually VGS, right? You have to use the ID equation to satisfy.
No, but sir, S source is connected to first and V3, right? And gate is also to calculate the voltage on the drain. We will have to look on the resistance that we can see in M2 through drain, right?
No,
and then
no, not exactly that way. We'll discuss that issue in the next class. Okay, we'll discuss that in the next class. Okay, thanks a lot. Let me stop it here now.